This is a treat for me, okay? I hope it might be a treat for you, but it's a treat for me. The reason is that when I give lectures now, because I don't teach formally anymore, it's at conferences where you get 15 minutes, 12 minutes and 3 minutes discussion. It's hopeless. Or you get 20 minutes, but 5 minutes of that is discussion. Even if you're a plenary speaker, you rarely get more than half an hour. So tonight, I've got maybe 50 minutes or so to talk about something that I think is obviously something I'm very active in at the moment. A lot of the work I've done this year, manuscripts I've been involved in, revolve around this particular issue. But I've been working on this issue since about 1998. Not full time. I've also worked in industry and I've had various other activities, but it's all sort of come together. And it's odd that it comes together in such a way that I'm now going to not throw out this basic law of stratigraphy, but point out that, in fact, it's not quite so straightforward, that it's not really a law after all, or a principle, if you like. And it's all to do with superposition, and I'll just run through what that is. But basically, it goes back to Steno and Smith, who independently in a way, but not quite independently, Steno was really the first, developed the basic law of stratigraphy. And if you're not familiar with that it is that sedimentary rocks are layered. That's the first thing undergraduates are taught. Sedimentary rocks are layered. This is a classic example. This is from Nash Point in South Wales. This is Lower Jurassic. It's the lias, the blue lias, which there's some dispute over the way the term lias came into common usage in stratigraphy. Some people say it's derived from a Middle French term, which has nothing to do with the geology whatsoever. Other people say it's simply the Middle English term for a hard limestone. I was taught as an undergraduate, it's because the lias, the Lower Jurassic, is best exposed in Dorset, where the local accent would say these rocks are full of layers. Lots and lots of layers. That's what I was taught. And that was actually one of the official explanations for the term. But look, what could be more sedimentary, more basic than seeing beautifully layered rocks like that? However, if you go in a bit closer, carefully of course, and people have been killed in this area in recent years by getting too close, you'll see that what appears to be nicely layered rock isn't in all cases quite so straightforward. You can see things are pinching and swelling, things are disappearing altogether. And it turns out that this style of sedimentary laying is much more common than we thought. It's not news, we've known about it, but it's only in the last few years we've been refining the chemistry of it, if you like, to understand what it is. So I'd like to remind you then of what the basic law of stratigraphy is, and it's Steno's principle of superposition, which says that a layer of sedimentary rock is older than the one overlying it, which is unnecessarily complicated. What it means is the layer above a layer must be younger than the layer to have been laid down on top of that layer. Okay, makes sense? That's the basic law of stratigraphy. William Smith, when he devised his laws, something like 150 years later or more, he called it his first law of stratigraphy. So undergraduates, virtually the first week they're a student, learn about the law of superposition, the first basic law of stratigraphy. Well, yes, it makes sense, doesn't it? You'll have bed number 1 laid down, then bed number 2, bed number 3, bed number 4, and bed number 5. Fair enough? Makes absolute sense. Of course, when you have igneous intrusions, they can force their way between layers or units of other rock. But we're not talking about igneous rock now. We're talking about sedimentary rocks which were deposited. They have to have been deposited on top of one another. They can be deformed in all sorts of ways. They can be deformed by compaction. They can be deformed by earthquake activity, for example, seismites. And of course, they can be caught up in mountain building and all sorts of things. But basically, that works. As long as they're in the right way up, they haven't been inverted, whatever, that law should work. So let's go back to the lias. In this case, the blue lias, the classic Mary Anning sequences in Dorset, or the same age rocks in South Wales, which are actually more extensively exposed, but are in facies which are less fossiliferous than the classic Dorset coast. These rocks in Dorset are probably the most studied and collected rocks in the world. 200 years plus of fossil collecting and study have gone into understanding the blue lias. But that is not layering, true layering. This is something else. And the blue lias, incidentally, perversely really, since it's the most studied, is a classic example of this type of diagenetic secondary layering, which has nothing to do with depositional processes. It's to do with the chemistry of the rocks, really. So it's a bit of a shock. And in fact, a friend of ours only reminded us quite recently that he went on a Cambridge University field trip as a guest and had to point out to the lecturer who was telling the first year students that these were classic layered rocks, that in fact they are not classic layered rocks. They're something else. And what I'm saying is that this is not normal superpositional development. So we have the first layer, the second layer, the third layer, the fourth layer, and the fifth layer. The fifth layer develops within an earlier one. So superposition doesn't work for a certain variety of sedimentary rocks, which turn out to be extremely common. So we have depositional beds and we have diagenetic beds. Usually these diagenetic beds are made of calcium carbonate, and that has been introduced as a cement from somewhere else very early on. It isn't something that takes place kilometers under the surface. It develops very early on, almost syn-depositionally, but it breaks the law of superposition. So such diagenetic bedding is very common throughout the Phanerozoic stratigraphic record, extremely common. However, Teresa Noll in Vienna, and Axel Municher and myself were involved in setting up a questionnaire to see how many sedimentologists appreciate that some bedding is not superpositional, it's diagenetic. The results came as a bit of a shock. It's coming out in a Geological special publication I'll refer to later. It turns out that it's where you live that matters. For example, North American geologists say no, bedding is never diagenetic. Australian geologists say the same thing in the survey. European, Middle Eastern, Asian geologists say no, and South American to some extent, say no, you can have some diagenetic bedding, but there are still large groupings of geologists who do not know about this. Okay? So by taking this work and saying Steno's wrong, Smith's wrong, and as you see later, Voltha, another basic law in stratigraphy, is wrong, we're trying to raise the temperature for everybody to realize this is a universal effect, and for some reason it's not widely taught in North America, or strangely in Australia. Right, so how widespread is it? Well, I could put in 100 slides, okay, from different parts of the world that Axel, myself and Teresa have compiled. There's just a few. These are upper Ordovician rocks from Anticosti Island in Gulf of St. Lawrence, basically in Canada. Largely undeformed Ordovician rocks, spectacularly exposed. We could go to the Holy Cross Mountains in Poland and see diagenetic bedding like this of Upper Devonian age. We could go to the Silurian of Sweden, Gotland in fact, very much like the Wenlock limestones in this area, very, very similar, but better exposed than in this area. And that's diagenetic bedding as well. We could, now most of these are associated with mudstones that we're seeing limestone beds separated by basically shales, okay? And that's the normal situation. In some cases, it can actually occur in coarser grain sediments. This is the upper greensand from Sandown in the Isle of Wight, and we've got diagenetic bedding features in here. These discontinuous, sometimes sheet-like beds, which have been introduced irrespective, if you like, of superposition. They didn't know they had to follow Steno's law. So, when did this kick off? Really, it's about 60 years ago. Tony Hallam, then at Oxford, later a professor for many years at Birmingham, and someone who Ian Fairchild would have known very well, Tony Hallam said there's something strange about these Jurassic rocks in Britain. I wonder if the bedding is diagenetic. But we didn't have a mechanism for explaining that until more recently. But then Axel Municher and his PhD supervisor, Sampelben, came along, and they were looking at the Silurian of Gotland. Sue and I have been to these outcrops just last year. But here is the same facies in the Wenlock limestone in this area. These nodular to sheet-like thin-bedded limestones separated by clays, usually shaly clays. So this was a seminal paper that was published in 1996, but not widely read in, for example, North America. It's in a journal which is even then in Europe wasn't widely read, but certainly has never been widely read in the US. So they didn't pick up on it. And still haven't picked up on it, most people, it seems. Right, so what Axel did was he was intrigued by these thin limestones that sometimes form beautiful sheets, ideal for house building or building walls, for example. Other times they'd pass into nodules. So he started to look at them. And one of the things he discovered was that when he put them under the electron microscope and etched the crystals, and these are very small crystals, this would be about 10 microns. So 10 microns is a 30th of the thickness of a human hair. So these are very small crystals. He noticed they were full of lots of pits, cubic, hexagonal pits, elongate pits, like small needles. But he was also aware, because he'd been working with another geologist, Hildegard Westphal, who was looking at the diagenesis of muds from the Bahamas. And her work showed that as these aragonite-rich muds, and I'll come on to what aragonite is in a second, as these aragonite-rich muds aged, as they became modified during early burial, very shallow burial, meters or so, tens of meters at the most in most cases, the aragonite was dissolving and being replaced by calcite crystals. Here you can still see some of the relic aragonite needles. Here, all the aragonite's gone, but you've got lots of these pits where the aragonite needles were. And Axel made the jump, and he said, but that's what I'm seeing in these strange pits. And a lot of subsequent work was done to refine that, using stable isotopes, using all sorts of techniques. So he said, surely that means that diagenetic bedding like this has somehow come about by the recrystallization of aragonite, forming beds where there weren't originally any limestone beds. In other words, these sequences were basically all shale with a lot of dispersed aragonite, but the aragonite dissolved, was locally moved around and formed sheets. That was his idea. A lot of people were perplexed by it, but over the following years, just put a little plug in. This is my hammer. I'm a bad boy. I should put a scale, proper scaling pictures, but I didn't have a decent scale with me that day. I've been using the hammer for over 50 years. Same hammer, I got a pair of them. So they haven't always been in use. But that's when we used to make things that really lasted. So I've been using those hammers, not every day, but they've had a pasting over the years. And I've still got them, and they're still perfectly useful hammers. There we are. I'm very keen on my hammers. I'm cherish them. I've actually been using them for more than 50 years, maybe 55 years in one case. What do we know about these characteristics of these limestones? They're called LMAs, limestone marl alternations, because the shale layers in here are rich in calcium carbonate, so we call them a marl. A carbonate-rich mud rock is a marl, whereas these are fine-grained, almost pure limestones. Here's some of the key points that over the last 30, 40 years we've come to define these limestones. They're associated with lower energy offshore to deeper basin settings. Sometimes they can be associated with protected low energy lagoons. they're associated with mud rocks, fine-grained sediments. Secondly, the bedding, as you've already seen, could commonly be traced into nodular beds. These can be traced into perfect parallel sheets. Other places, they just disappear into nodules, telling us there's something odd about their deposition. They're typically composed of very fine-grained carbonate crystals, less than 20 microns in size. The carbon and oxygen stable isotopes, I can explain all this later, but what that's telling us is carbon and oxygen isotope ratios we see in these carbonates are exactly what we would expect if the carbonate had precipitated from seawater at that time. These ratios have varied through time on short-term fluctuations and long-term fluctuations. But there are ways we can determine what the carbon and oxygen composition was of something precipitating out from a Silurian seawater or Carboniferous seawater, Ordovician seawater. It gets more difficult in the Ordovician. But certainly younger rocks, we can do that reliably. And what we know is these precipitated out from seawater at the time, but probably as seawater in the pores in the sediment, the shallow buried sediment. The limestone beds show evidence of being locally reworked, but not often. And that suggests that they were forming near the sea floor so that they get reworked by storms, by big currents and so forth. But interestingly, that we know that back in the early Paleozoic, they were forming very, very near the sediment surface. And I'll come on and expand on that later. The limestone layers show no evidence of compaction at all. Even the most delicate fossils are not compacted. So they must have been, even types of pollen grains don't get compacted. It must mean that the limestone around them formed as quite a rigid, protected, cemented zone early on, before compaction. And yet when you look in the intervening beds, they've suffered very considerable compaction. So these limestone units are forming very early, near the seafloor surface, before any compaction. The associated beds, particularly the shales in between, but to some extent the limestones as well, have been severely depleted in aragonitic fossils. There's a little drawing out there of what the Silurian sea floor looked like. It's wrong. That's what we thought the Silurian sea floor looked like, because something's missing. And what's missing is aragonite. It's been removed. And also, these limestones are associated commonly with trace fossils, which indicate an early degree of lithification. A particular group of trace fossils, things like Thalassinoides, which you'll see in any limestone marl succession, they have been known to indicate that the sediment is getting stiff. Not necessarily hard and lithified yet, but getting stiff. So there's all sorts of evidence we can use and criteria we can use to identify them. Now, aragonite. What's aragonite? Basically, aragonite is a strontium-rich form of calcium carbonate that has a slightly different crystalline structure to calcite. Okay? So the important thing is that it's actually less stable than calcium carbonate. The solubility contrast between aragonite, which is calcium carbonate with a bit of strontium, from calcite, which is calcium carbonate with very little, if any, strontium, the solubility difference is so great, you can dissolve aragonite and precipitate calcite next to it. There's a big contrast in the solubility. It's a relatively unstable calcium carbonate mineral, and yet it's one of the most abundant minerals that animals use to make their shells or whatever, mollusks, corals, and so forth. Now, Munica and co-workers thought that the aragonite mud, that the aragonite they were seeing that had recrystallized into those layers, came from aragonite mud. It was deposited as aragonite mud. And we do see places today where aragonite mud will precipitate out of seawater, the Bahamas, for example. But under quite special circumstances, but it does happen. Most of the aragonite that ends up in the sea, in sediments, is coming from calcareous invertebrates, particularly the mollusks and the corals, and even some plants, the codiacin and dasyclad algae, also produce a lot of aragonite. deliberately, but you can also have it forming abiotically. The trouble with thinking that all the mud you're seeing in those layers has come from aragonite mud is that there have been times in the past when aragonite, both biotic aragonite and abiotically or chemogenically produced aragonite, just precipitates out of seawater like salt will in arid conditions, was actually not very common. So we have to find another source for all this aragonite. There is a little place in Utah called aragonite, funnily enough, but I like to come back to place the term aragonite right at the end. There's a more abundant source of aragonite throughout the geological record, and it is from mollusks. The mollusks that you don't see. Okay? The Wenlock, if you'd swum in the Wenlock limestone sea, you would have seen a lot of aragonitic mollusks. But you don't see them anymore. And let me elaborate on that. So let's just pick two examples of the story of how we produce these layers. We'll pick one example from the Silurian of Gotland, the same age as the Wenlock limestones here. And we'll go back to the Blue Lias of South Wales. Now, if you're not interested in the chemistry and the sedimentology, let's look at the fossil evidence for all this and just how skewed the whole fossil record is. If you look at the Silurian faunas of Gotland, you find, I didn't feel good about drawing a moving or a live-looking trilobite on this, but we could put trilobites in here, you know, the deadly locust and things like this. What we see in the Silurian is we see corals, we see bryozoans, we see brachiopods. This one's actually from Wenlock limestone. So if we go anywhere in the world where we see Silurian limestones, Gotland's the best place. Wenlock's another good place. The Great Lakes area of North America is another good place to see the Silurian. You will see the same basic components: brachiopods, trilobites, crinoids, corals, and bryozoans. Now today, the corals are made of aragonite. In the Paleozoic, they were made of calcite. In fact, all of these are made of calcite. They're very stable. So that would be a typical, I mean, you just look at the picture out there on the poster. That's the typical picture of a Silurian seafloor, dominated by brachiopods, the crinoids, corals, and some bryozoans. That's what I was taught. That's what the textbooks still tell you, surprisingly. However, that has turned out not to be the case. If you look at cemeteries, Roman cemeteries, you'll find there's a lot of babies buried there and young children and a lot of older people. People in their teens into the 20s, 30s, very few, because they were healthy. The highest death rates were with infant mortality and old people, right? You go to Pompeii, you find an exact picture of what the population age structure was, because they were all killed at once. Apparently, you find fewer old people in Pompeii than you'd expect, because the older people had more money and they escaped. That's a rider to that story, but you get the general picture. If you do something nasty to the seafloor, like in this case at Mulbus, the Silurian in Gotland, there's a volcanic ash layer here, a bentonite. You have bentonites in the local Silurian around here as well. Well, bentonite, under the right conditions, will release a lot of silica, and that silica will replace aragonite. When people started studying the faunas of Mulbus, they found thousands and thousands and thousands just in these pits of beautifully preserved fossils, many of them in life position. The things you find in the Wenlock are normally, particularly the brachiopods and things like this, the crinoids, not in life position. They've broken up and moved around. Here we found that things have been found in life position. So you've just buried, killed off instantly the fauna. And the fauna is dominated by small bivalves. And these bivalves today, those families, those groups of bivalves today, are always aragonitic. So we have removed the aragonitic component. I think the Mulbus collection contains at least 7,000 gastropods. No one studied in any detail. It isn't just these types of burrowing bivalves which were common, it was also gastropods living on the seafloor as well. So this is what we thought a typical Silurian assemblage was like. This is what it was really like. Abundant species. In fact, the diversity is all in the mollusks. You can calculate species richness and so forth from these rocks because the faunas have been extraordinarily well documented. And what we can show is there has been 100-fold decrease, not 100%, 100-fold decrease in the abundance of mollusks when you go from a life assemblage buried by volcanic ash to what you thought was the assemblage. So the aragonites disappeared. This is just showing you, these are bimineralic, they have calcite and aragonite layers. This is fossils which were originally calcite, these are fossils which were originally aragonite. So if you look at the life assemblage, it's dominated by aragonitic forms. If you look at the death assemblage, all of this change is the removal of aragonite. In other words, many textbooks in paleontology have got it wrong. This has been known for decades, okay? That's releasing huge amounts of aragonite early on. If we go to the blue lias, by the way, these are called skeletal Lagerstätten. The term Lagerstätten means fossil load. You may know about the Burgess Shale, where you find all these soft-bodied animals. That's a Lagerstätten. You're seeing enormous diversity in the fossils that you didn't know were there. In those cases, it's usually where you get the soft parts preserved. This is a skeletal Lagerstätten. This is where you get shelly fossils you never knew existed. That's why they turn up lots of new species. Taxonomists have a whale of a time when they find these, because they can set up all these new species. Because they'd never been seen before unless some event had captured them. So this is the classic Jurassic fauna. If you go to South Wales or you go to Mary Anning's rocks and you're just looking at the invertebrates, you'll find a limited number of bivalves. It's what people collect, the Gryphaeas, the Pinnas, the Plagistomas and so forth. And everybody for 200 years was perfectly happy with that. It turned out because under the Ford Motor Engine factory in Bridgend, now I think largely closed, when they were building the excavations, they found fantastic silicified faunas again. And those faunas were completely different to these. You still get these in the silicified fauna, in life position as well, many of them, but you have a greater diversity, and it's again infaunal bivalves which live in the sediment and gastropods. You get all the usual things, you get the usual Gryphaea and the Pinna and the Plagistoma, but you now get increased diversity. So once again, we're seeing missing mollusks for the first time. That's the source of the aragonite for making most of these limestones. So what? Well, so what? This effect of aragonite dissolution, and I'll come on to in a second how it happens, this reduces biodiversity estimates drastically. There are some estimates in the States which say that if you look at biodiversity through the whole of the Phanerozoic, it's been reduced by between 19 and 42% because of this process. So diversity was much greater in the Phanerozoic than we ever thought. Paleontologists and paleoecologists don't like being told that, especially the paleoecologists, because they've missed the full story. Where it becomes an issue for paleoecology is that it removes major parts of the trophic structure. The greatest diversity of mollusks is often in the infauna living in the sediment, but that's always removed. There's also incredible diversity in gastropods, especially in the microgastropods. And they've disappeared as well. There are some odd things, which I'll come on to in a second. You do get preserved in the blue lias a lot of deep burrowing former aragonitic bivalves. Well, that breaks the rule then, Or does it? I'll come on to that in a second. Right, the mechanism, okay? Little bit of chemistry, not too much. This is based on multiple studies. Dozens of studies by geochemists have been looking at what happens in the upper parts of the sediment column, the first few meters or whatever. So the biogeochemistry of this is known in excruciating detail. Multiple studies have found the same results. And what they find is this. The upper part of the sediment layer, that's the layer those little bivalves are living in, is oxygenated. Okay, it's oxygenated because oxygen diffuses down from the seawater, and also bioturbation helps, and burrowing helps introduce oxygen into the sediment as well. In low energy environments, it's not just fine-grained material which is settling out, it's also a lot of organic matter. And that organic matter is attacked by oxidative bacteria. And very quickly, all the oxygen is used up. So at some depth in the sediment, it might be meters in the sand, which is very permeable, and there's not a lot of organic matter gets deposited in sandy areas because we're talking about very fine organic particles. But in muds, this can be a very, very narrow zone before you get into the next zone, which is called the sulfate reduction zone. In this, the bacteria using oxygen as an energy source. But when all the oxygen is used up, it can be millimeters down, can be much deeper. But when all the oxygen is used up, the bacteria can use sulfate in seawater as an energy source called sulfate reduction. Now, I'm only picking on one type of bacterial process, lower down in the sediment. There are multiple zones here. You have methane oxidizers, you have methane producers, you have iron reducers and so forth. The real chemistry here is extremely complicated. But what seems to be crucial in understanding the loss of these fossils is the behavior of hydrogen sulfide. So the upper part, the oxygenated part, is called the TAZ, the taphonomically active zone. It's not a strict definition of it, but it's effectively the same thing. So this is the oxidized zone where things can live and they can extend their tubes, whatever, to get oxygen if need be. But lower down, there's no oxygen in the sediment. It's the sulfate-reducing bacteria are breaking down the organic matter, what's left of it. As part of their metabolism, they produce hydrogen sulfide. That's why if you dig a hole in a tidal mud flat, it smells of rotten eggs if you dig deep enough. Because hydrogen sulfide is being produced. That's the villain in this. Hydrogen sulfide is a toxic gas. In the oil industry, if you're on a rig and you can smell H2S, that's okay. If you suddenly can't smell H2S, you're going to die because it's a very dangerous gas, hydrogen sulfide. However, it's not dangerous at the amounts coming out of these seafloor sediments, okay? We don't need to worry about it. What happens to the hydrogen sulfide is it diffuses upwards into the oxygenated zone, and it turns into, it's oxidized into sulfuric acid. Now, it isn't that you can stick your finger in a mud flat and you feel it burning away. We're not talking about acids of that strength. We're talking about an acid which is strong enough, however, to dissolve aragonite quite quickly, within tens of years, certainly within hundreds of years, probably a few tens of years. It depends on so many variables. So basically, bacterial action in here is producing a gas which turns into an acid and dissolves the aragonite. So if you have aragonitic fossils in here, shells in your initial sediment, they'll be removed. Except we still find former aragonitic forms like this. In the Jurassic, it would be Phyllodemia pluromia. You can go to the cliffs in the Jurassic and you will see them still in their life position. So that breaks the rule. No, because this is a group of bivalves that actually lives below in the sulfate reduction zone because they keep in contact with their very long siphons. The reason they elongate is they've got very long siphons that go right up to get oxygen from the surface. So in fact, the exception to the rule, these are both Jurassic, proves the model. So basically, as the sediment accumulates and these zones move up, you destroy all the aragonite. Well, you sort of destroy all the aragonite. Ammonites. If you go to the Liassic of South Wales, somewhere like Southern Down, for example, which I'll come into right at the end, there were ammonites there. But the only ammonite fossils you normally find, it's different in the Dorset Blue Lias for a variety of reasons. But in South Wales, this is what you see, outlines of the ammonites. Sometimes you'll find a good mold of an ammonite, but always big ones, no little ones, or very, very rarely little ones. The big ones, the ones that had thick shells and partially survived all this dissolution. But look what's happening to them. Initially, when that ammonite was on the seafloor, it was colonized by Gryphaeas. Now, Gryphaea, the devil's toenail, one of the most collected fossils in the world, probably. When it was a veliger, when it was a spat floating around, it had to settle on a hard substrate. In adult life, they lost that cementedness, unlike oysters today. So they were looking for somewhere hard to live on. So they would be living around the edges of ammonites and colonizing them. So when we see the ammonites gone, but we have a ghost of the ammonite by where these little baby oyster-like bivalves lived. These are bimineralic, so that we still can see evidence of them because they have a calcitic layer. So if all we end up with is just these ghosts, telling us that we've lost the aragonite. Right, so we're losing aragonite from here. It's going into solution, and all the evidence points to the fact that it diffuses down into the sulfate reduction zone, which is a zone of alkalinity, higher pH, and the calcite precipitates. So we have donor beds and receptor beds, okay? And that seems to be what's going on. All these fossils have disappeared. Steno didn't know this, Smith didn't know this. But that seems to be one of the major sources of this. Axel and I disagree on the provenance of the aragonite originally. He thinks it's mainly carbonate mud. I think it's mainly mollusk. We've been working together for some years. We don't agree on many things to do with this, but this basic overall story we agree with. But we've never fallen out. Despite popular culture thinking scientists fall out over their ideas, most scientists don't fall out. They just try and work through their difficulties, you know. Should make good diplomats, but I think that's probably a very bad idea. So here we have our diagenetic beds. We have a donor layer and a receptor layer. So we lost aragonite from here, and it was precipitated down in here. What's that really mean? The bedding planes, which the textbooks, all the websites say a bedding plane is a depositional surface representing some change in environment. So you see a break, maybe a hiatus. No, these are cementation fronts. They're just zones of sharply divided zones where carbonate was diffusing and precipitating out. They're not bedding planes in the classic sense. They're cementation fronts. Okay? Well, that's what all the evidence suggests. Now, there are other things going on as well. For example, if you look at some of these nodules, they've often got, and there's one I showed you right at the beginning, was really very elongate. But when you look closely, and sometimes weathering brings this out, you realize that inside every elliptical nodule is a spherical nodule. And when you examine the spherical nodule, it's often got a very open packed, what are called clay cages. This is calcite, again, 10 microns. These are calcite crystals, and these are clays. And as the carbonate precipitated out in the original, what was to become a shale, the original mud, it pushed aside the clay plates. So you get what's called house of cards fabric. Loose sort of, gaps between the cards. The clay plates are like the cards. But when you look in the outer parts of the nodules, which are not spherical, they're more elliptical, you find different textures. In some cases, you find the clay much more compacted together because that outer part had formed later during burial, not initially before compaction, but later on. So the nodules are not straightforward. You have to determine exactly which part of the story you're dealing with. So the argument is that these formed before any compaction, so they displaced the clays like this. These outer parts formed when there was more compaction taking place later on. Okay, if you want to get in the chemistry, I sort of slipped this in for Ian if he'd been here, Ian Fairchild. And this is work that was done by Nasser Azani. There are some other studies as well. If you're interested in the chemistry, then this is the only chemistry I'm now going to put in. If you look at the carbon and oxygen isotopes of the nodules and the beds, the inner parts of the nodules, the inner parts of the beds, they plot in this field here. It's only got one dot in it, but I just made it, it's a field. This is where the overall field of what the carbon and oxygen isotope composition would be from Jurassic seawater. How the hell do you know that? Well, you can analyze fossils which were originally calcite, which have never undergone any alteration. There are techniques for doing that. The gryphia, the abundant gryphias you get in the Jurassic, can be used to working out what the seawater composition was in terms of these isotopes. And nicely, the inner parts of the nodules from the Jurassic in South Wales plot within that field. But if you look at the outer parts of the nodules, they plot differently. So they've had a slightly different origin. They were, after all, after quite a bit of compaction. There aren't many studies that have looked at this carefully, but the suggestion is that because these oxygen isotopes are lighter, they've got more oxygen-16 in them. This is a ratio of oxygen-16 to oxygen-18. Basically, if you go in this direction, you've got higher temperatures. So that would fit in well with the outer parts of the nodules having formed during deeper burial. But the details of all that, there haven't been enough studies done on it to pin that down yet. People do a staggering amount of isotope work on LMAs to work out changes in seawater composition. But they don't distinguish whether they're often in the outer part or the inner part of these nodules or beds. But it's showing you that these nodules and beds are formed over a long period of time, both before compaction and to some extent afterwards. So it's a bit more complicated than you might think. Okay, Paul, good question. Why would you have all this regular spacing? Sometimes they're very close together, as you've seen earlier. Sometimes they're separated by a big thick shale. People get interested in that. People have built their whole careers doing statistics on these rocks, Fourier analysis, and they are able to identify Milankovitch orbital forcing, the things which causes the ice ages, the precession, the obliquity, the eccentricity. They can decipher them from these rocks. Well, that's one camp. The pure sedimentologists say, whoa, it's much more complicated than that. You can't do that. And there's a bit of an impasse between the two groups. So some are saying that variations in the layering is being caused by variations in the sedimentation rate or the fluxes of clays, siliciclastics coming in relative to aragonite, or in the supply of organic matter, which is the ultimate control on these microbial reactions. But in fact, if you make a list of all the variables that controls the diagenetic system I'm talking about, and this is from a paper I did with Axel and Teresa last year, those are the main controls. It's complicated. Yes, there may have been astronomical shifts in the global climate. Exactly how they impact on all these variables is not known. Maybe it'll never be known. So we have two groups of people. Some were saying this is all controlled by cosmic forces or, changes in the Earth's orbit. And others who say, it's complicated, take it easy now before you can tell us, it rained on the third Wednesday after Lent in the early Jurassic. You've got to be careful how you do this. The truth, of course, when it comes out, is that it'll be a mixture of these allogenic controls, these perhaps orbital forcing or major external controls, as against autogenic processes. And the autogenic processes are not fully understood. One possibility is that it's controlled by self-organization. That's the in thing at the moment. Self-organization, chemical self-organization produces zones of depletion and cementation. but that's currently being modeled to try and make some sense out of it. I don't think the models are running all the variables, but I would always say that. But where does the carbonate go? Some of it must be backfluxed to the world ocean. All the bioturbations releasing all that aragonite back into the water column, probably. Diffusion back into the water column. There's some evidence from the Bahamas today, looking at sediments in the Bahamas, that it's a closed system. Latest evidence for the Bahamas is saying it's sometimes closed and sometimes open. Who cares? Well, we have to worry about carbon, don't we? Apparently, we have to, quite rightly so. We're in a mess. We're in a worse mess than we ever thought. Who cares? It has been reported that the dissolution of benthic carbonate, aragonite, the mechanisms I'm talking about, due to the oxidation of sulfides, oxidation of hydrogen sulfide gas, could source as much as 25% of the dissolved inorganic carbon in the ocean. So if you're doing carbon budgets, you have to take this into account, okay? Nothing you can do about it, but you need to take it into account in your sums as you do it. Oops, this is one of the more detailed studies by Sun and Turchin, and they were working out the global carbon budget. Important stuff, okay? They acknowledge the likelihood of this dissolution in the upper part of the sediment column, but unfortunately, all their data ignored what's happening in the top 1.5 meters. The trouble is, we think most of this is this refluxing, if you like, of the carbon from the calcium carbonate. The aragonite dissolves, releases carbon dioxide, and it goes into the water column. We think that most of it's actually taking place in the bit they haven't included in their models. No disrespect to them. There's a reason why we don't know that, because nobody has systematically sampled that depth of sediment globally, and there's a very sad reason for it. Okay, where does this happen? Quickly then, where does this happen? How could we measure where it's happening in deep time? Any suggestions? How could we possibly know where this cementation is occurring in deep time? I mean, we haven't even measured it accurately in modern sediments. There's an attempt to do it now off the northwest coast of Australia if it gets funded. I hate boats. I'm not going on that cruise. I've made it quite clear. I look at the data, but I ain't going out on a boat or ship, if you like, whatever, either way. But how could we measure it? Well, nature always provides a way. And that is, you can do geochemical modeling. And this is the latest paper that's just come out in the journal Geochemica Cosmochemica Acta, which is a serious sounding journal, and it is, scientific journal. There it's been suggested that a lot of this diagenesis is taking place in the upper 30 meters of the sediment column. Earlier estimates from the same data set, but involving less modeling, suggested it's about 100 meters. The trouble is that the settings that have been studied, just one set of cores from the Bahamas, are not the settings where we know LMAs naturally form, which is in shallower water. So it's not quite the right place. There is a lot of stratigraphic evidence that suggests the depth in a sediment pile is shallow, and it was much, much, much shallower in deep time. This again is where the fossils come in and so forth. So the depth to which you get these geochemical zones, so this is where we're losing aragonite, this is where it's reprecipitating as calcite to give you diagenetic bedding, okay? The depth today is very variable. It all depends on how much oxygen you've got in the upper layer. And in low energy environments, muddy environments, a lot of organic matter, a lot of decay going on, it's oxygen diffusing in or being introduced through burrowing. And many organisms, particularly those little bivalves which have all disappeared, whether we're in the Silurian, the Jurassic or whatever, it's these ones which you don't see any evidence of in deep time very often, are the ones which are helping oxygenate the sediment, and many other organisms as well, of course. But anything that burrows and churns can mix the oxygen in. Right. Now then, that looks complicated, but I can break it down into this. Since the late Ordovician, the average depth, what's an average with the variability we see in the natural world, what's an average? Well, let's just go with this. In low energy environments, an average, which most people wouldn't quibble too much with, depending on all these variables, but an average, is about, say, 30 centimeters or more. And that's been the case since the late Ordovician. Now then, you go back to the mid-Ordovician, and we can look at the depth of burrowing, we can look at the trace fossils. And we know that the depth of burrowing then, because diversity was a lot less, the depth of burrowing was only 6 centimeters. Okay? So in the Silurian, it had increased. It was almost like modern depths. But go back into the Ordovician, and it was, in muddy environments, was only like that. Go back in the Cambrian, and it was less than 3 centimeters. Nothing was burrowing in fine-grained sediment more than 3 centimeters. Well then, let's go back one. So that means that you weren't heavily oxygenating in the Cambrian anything below 3 centimeters. In the early Ordovician, 6 centimeters. And by the late Ordovician, 30 centimeters. So if this depth to the sulfate reduction zone is deepening during that time interval, does that mean, because this is the sulfate reduction zone is where the carbonate precipitates out, that was lowering? How on earth could we measure that? Well, there is a way of looking at it. And that is using what the storms were doing. If you go into the Cambrian, the sulfate reduction zone was about 3 centimeters down. So we were getting cementation as shallow as 3 centimeters, the model says. That's pretty easy to rework that. And we find the seafloor littered with reworked bits of early cemented limestone. And as you go through time, you see a shift. Two things, I'll go through each stage with you now. These are what are called flat pebble breccias. It's where the cemented zone's been reworked by storms. These are hard grounds, okay? So let's have a look what we found happens during the early Paleozoic. In the Cambrian, when burrowing depth was 3 centimeters or less, we found the seafloor in certain environments littered, low energy environments, littered with fragments of cemented limestone. They're called flat pebble breccias. And they peak in the Cambrian. And then they disappear. Okay? There are two types of flat pebble breccias. These are the open marine flat pebble breccias. Shallow water, very shallow water flat pebble breccias are basically reworked bedrocks. But these are different. So these amazing things which have troubled geologists for generations. Why are they so common at this interval? Well, if these are basically very thin LMAs, thin little limestone layers, and they're forming only a few centimeters down, they're going to get reworked pretty often. And because they get reworked pretty often, they'll have a short residence time and they won't develop much of a thickness. Okay, move on. If we go to the Ordovician, we find the flat pebbles have been replaced by fat pebbles. They're still pebbles, were reworked by storms, but they're much chunkier. Evidence they were reworked is you can find crinoid holdfasts were attached to them. So these were forming in the sediment, probably 6 centimeters down, but therefore, because they're a bit deeper, they were reworked less often. So they got a bit bigger, but they were still being reworked. Now then, if you move on to the early Ordovician, particularly in mid-Ordovician, that is the peak for hard grounds. Hard grounds are cemented sea floors. No one's understood why there's this sudden peak of hard grounds after the flat pebble peak. It's easy to explain as limestone marl alternations and burrowing because the depth of burrowing was a bit deeper. So the sediment was disturbed less often and the layers got thicker because they were sitting there for longer before a really big storm came along or a tsunami. Now they were so thick, they weren't all broken up. They were just, the mud was planed off and it left a cemented layer. And they became the seafloor. If you'd gone to the Ordovician in North America and the seafloor, which was all under shallow water North America, you would have seen huge areas of the seafloor all cemented up, only in the mid to late Ordovician. Go back in time, you would have seen these rather fat pebbles. Go back in time again, the same environments, you would have found flake breccias. Now, the next step is, why did these disappear? Well, we know that by the late Ordovician, there was a sudden deepening from 6 centimeters to 30 centimeters. So the sulfate reduction zone was now much deeper in the sediment and was disturbed hardly ever. Now, even in younger, and this is when we see the development of prominent limestone marl alternations, because this cemented layer is getting disturbed far less. You do find it being disturbed. There are some famous horizons in the British Jurassic, for example, the coinstone layers and things like this, where you get hard grounds which represent where thick limestone, diagenetic limestones have been exhumed. They do occur. The chalk hard grounds are of that origin. So we do see them, but they're much rarer as the depth of burrowing. So in other words, the whole story of where this diagenetic limestone layers is forming is controlled by the depth of burrowing. And evolution gave us deeper and deeper burrowers, so it went down. And that explains the sudden disappearance of hard grounds and the appearance and disappearance also of flat pebble breccias. So we got an idea. The problem is, where is it happening today? The geochemists have understood the chemistry of this, but where are we seeing all these cemented layers today? We don't have records of them very well today. And the reason is rather sad. The reason is that if you try to sample using a box or gravity corer, it won't break through them. So we don't get any samples back where they do occur. All right, core it. The trouble is that when you start coring through thin lithified layers, you get biscuiting. All the soft sediment is removed during the coring, is caught up in the drawing back the drilling fluid. And all these thin lithified layers just get all broken into a mush. Sometimes they look like biscuits, hence the term biscuiting. Other times they get mixed in with a lot of the fine-grained sediment. And I've never used this, but it's called biscuits and gravy. The corers call it biscuit. People who do these ocean floor drilling programs. Now, hundreds of millions of pounds have been spent in the last 50 years or so on the ocean drilling program. That's how we know so much about ancient climates and ancient oceans. But they don't sample the upper 1.5 meters anyway. So we can't show these processes are taking place widely today because nobody's looked. Okay, nobody's systematically looked. So there's a project going on now, still being compiled, to specifically go off the northwest Australian shelf and say, look, forget 5 kilometers down. Let's just have a good look at what's happening in the top 100 meters, certainly the top 1.5 meters. And it's sad. Maybe we'll get. See, we have the chemistry to explain it, but we don't have the physical evidence from today because we haven't looked properly for it. Bizarre as it may sound. Right, finish off. If this is diagenetic process is really important, have you noticed one thing about all the evidence? It's all coming from shale limestone outcrops. Shale limestone outcrops. Because if you have a shale sequence and you develop these nice little limestone layers, you can see them, okay? You can measure them easily. What about ordinary limestones? Surely these processes are taking place in any fine-grained limestone, surely, which would have had aragonite. Well, if you go to the Carboniferous of Three Cliffs Bay in the Gower, you can go from the lower limestone shales, the name gives it away, the Kevin-Bryn shales, and you can see diagenetic bedding in there. You go 20 meters higher up where there's no shale, you don't see any of these effects. And that troubled me for a long time. I wouldn't say I lost sleep over it, but it certainly bothered me. However, the problem had been discussed years before in a paper which none of us took as seriously as we should have, by the then guru of carbonate sedimentology, Robin Bathurst. He did a paper, a very long, detailed paper, without any chemistry, just observation. And he said that he'd noticed that in many fine-grained limestone sequences, not shale limestone sequences, limestone sequences, he saw what he called couplets. He saw beds of limestone, which when he examined them showed little or no compaction, so they must have been cemented up really early, with layers which were highly compacted. And he came up with this idea of stratified cementation. And he said, look, what's happening is in a pile of sediment, you've got zones of early cementation. Of course we have. We knew it from LMAs. We just hadn't put all the jigsaw pieces together. And he said, in the bits that weren't as well cemented, compaction reduces the volume because of chemical and particularly chemical compaction, and you end up with a highly compressed layer. And most of these bedding planes are forming within this highly compressed layer here. I've never ever seen anybody discuss couplet bedding. Ever. Okay? Shame to say, I don't think the textbook I wrote in 1990 with Maurice Tucker, which turned out to be the main textbook in the field, and it's still used, which is worrying because it's 34 years old and it's so out of date. But I don't think we discussed this properly either. But Bathurst nailed it. He didn't discuss the mechanisms. He didn't have all the evidence of the missing aragonite. He didn't have the chemical models we now have. But he says this was going on. But we didn't take any notice of that. Okay, so this is where there was early cementation of a limestone. This is where you've had extreme compaction because it wasn't as cemented, and you end up with layering like this, Bathurst couplets. So you nailed it. Well, there's a lot of other things going on, okay? There are bedding, which is purely due to pressure solution and stylolite development, called pseudo-bedding. That's another story we haven't got time to go into. Right, let's put it all in context. One of the most important books on stratigraphy in the last century were the 3 editions of The Nature of the Stratigraphical Record by Derek Ager. It's a very anecdotal book, but a very clever book. When I'm involved in doing a new edition after, 31 years. He's no longer with us, Derek Ager. So I thought, well, we've moved on a lot since then. It's going to be anecdotal. I won't learn anything because I read it, the first edition in 73. Boy, it's still pertinent what he says in there. But ironically, in a way, on the cover of the book, on the cover of the book, he has that outcrop at Southern Down of the Lias. What he didn't know is none of that is true bedding. That's all diagenetic bedding. So all of this from Sue's head, starting here, that's all diagenetic bedding. Whereas in the bottom part here, this is slightly different. It's Bathurst couplet bedding. So now, people have been going to these outcrops for generations. It's a classic outcrop to take students to in South Wales. But now we know that it's actually one of the best places in the world for seeing different types of diagenetic bedding. LMAs, limestone marl alternations, all diagenetic limestone, and this is primary bedding, but it's been modified by early cementation. So if we go in close, we find these fissile interlayers where there's been considerable compaction, and in between we have fine-grained limestone with no compaction, early cemented. I have never seen a paper discussing couplet bedding. I mean, have I not looked in the right places? Did we completely ignore Robin Bathurst? Robin Bathurst is my PhD examiner, not my supervisor, my examiner. And he's no longer with us. But he'd really smiled to think, it's taken you lot, 37 years to catch up with something he suggested. But we didn't understand the mechanisms then. This is what that outcrop looks like. This is uncompacted limestone. A lot of it has been cemented early, and here you've got the compacted layer. Right, one last thing. Since we're proving that the basic law of stratigraphy is incorrect, let's go the whole hog and have another go. One of the basic rules of sedimentology is Volther's law. Volther's law states that in a vertical sequence of sedimentary facies, rock types, what we see is the result of a series of depositional environments that are or were laterally adjacent to each other. What's that mean? Well, it's very simple. Taken from a website from the University of Austin. It says that here's your depth gradient for your sediments. You have sand, you have mud, and you have limestone. But as sea level changes and these facies belts migrate, you can have, for example, the shale overlain by a sandstone if it's a shallowing upward sequence, or the limestone overlain by a shale in a shallowing upward sequence, the reverse in a transgressive or deepening upward sequence. That's a basic thing in sedimentology. When you teach sedimentology, Wolfer's law is the basic thing you teach. The trouble is that in LMAs, the limestone and the shales were never next to one another in a depositional gradient, so it doesn't work. Wolfer's law doesn't work for LMA sequences. That'd be okay if they were rare, but they're not rare, they're extremely common. Now then, the German geologist Max Semper said in 1916, we know nothing about the processes, and in this complete and utter ignorance lies, I believe, the cause of the fact that the bedding planes are usually treated as something quite evident in need of no explanation. We now know in LMAs the bedding planes are not bedding planes at all. They're actually diagenetic fronts, cementation fronts. They don't obey superposition, and the lithologies don't obey Wolfer's laws. It's okay as long as we know that, but we can't go on telling students these are laws. They're not. They're not universal. In Old German, they have these words, Schichtung and Bankung, which means sedimentary and diagenetic bedding. So in a way, ingrained in the German sedimentological psyche has been an awareness of these complications. Hardly surprising that much of the work on LMAs has been done in Germany, particularly by Axel Miniker and co-workers. So I thought, Semper, another guy, if you have this thing in the Times, who would you invite to a dinner party? I'd certainly invite Semper now. I'd invite Smith and possibly Steno. I wouldn't rub it in, you write most of the time, however. But I discovered today that Max Semper is best known for saying the idea of continental drift was rubbish. And he did so in a very, very hard way when he attacked Wegener's ideas of continental drift. So he isn't known for being a very insightful sedimentologist. He's been known for a very aggressive anti-continental drift person. So there we are. To conclude, for a significant volume of the stratigraphic record, Steno's principle of superposition, in other words, Smith's first law, does not strictly apply, and neither does Wolfer's law. Now, this is coming out in a paper, a special publication of the GeolSoc. Neil Davis at Cambridge has been asking people to think about what bedding really means. And so this contribution has gone into that book. So it probably won't...
Are you happy to take any questions?
Absolutely, yes.
Can I just ask, maybe you can ask a question, but I also want to ask, would it be possible to repeat the question because it'll come out
Okay.
on my and not.
Right.
Thank you. Thank you very much for...
Are we back on the recording?
We're back on the recording now.
Right.
Basically the compaction of the beds. You mentioned that it's almost uncompacted, the cemented bed, and the other bed is compacted. I just wondered two things. One, what's the approximate compression ratio? And secondly, showing I possibly misunderstand how these things work, would that actually represent the typical 30 centimetre bioturbation compressed in each case or not?
So the question is, how much compaction takes place because the interbeds between the limestones are heavily compacted, and is that in any way related to the depth of burrowing? The answer is we can't answer either question reliably like that. The amount of compaction is very variable. What a number of studies have done looking at the limestone beds is there's just no compaction. Even, as I said earlier, the most delicate fossils, even pollen, has not undergone any compaction in there, or virtually no compaction. Whereas in those limestones, there's been variable amounts of compaction. Sometimes you can still see much of the basic fabric, Other times it's been reduced by chemical compaction as well as physical compaction. And you've clearly perhaps a 10-fold reduction in thickness. The thickness of the shale layers didn't seem to bear any relationship to the burrowing depth. One of the things that I have to come clean on is that when I say it doesn't follow Steno's law, if you think about it, there's the seafloor, okay, and there at some depth the carbonate's beginning to form. But the seafloor is degrading, and this thing is also thickening. So it's quite likely that at times some of that carbonate was nucleating before the top of the overlying shale layer had another carbonate imposed within it. So you could say that it only partly breaks Steno's law, but we don't seem to see any relationship with the burrowing. But there's a very interesting point, because there have been attempts made to integrate ichnology, trace fossil studies, into understanding diagenetic layering, because trace fossils, we know they're tiered, different trace fossils burrow to different depths. So we can probably try and get a lot more information about the mechanisms of limestone formation from integrating trace fossils. Attempts to get funding for that work have not been successful, because funding goes towards climate change and energy transition, fair enough. Worryingly, even getting trace fossil experts interested has proved extremely difficult, and in fact has not achieved anything. But there's a great deal of mileage in looking at how the beds relate to the preservation and penetration of different types of traces. There's a really nice career, you could argue, there somewhere, but we haven't got the trace fossil people interested. And in fact, in the paper I mentioned right at the end, that may alienate quite a few of them when some of the things in there point out that there have been some mistaken issues about trace fossil occurrence because they haven't taken into account the development of these cemented layers. But so the answer to both questions is don't know, but we could find out a lot more easily.
Anyone else?
Just forming this question as I think about it. On land, carbonate, bicarbonate transitions are quite important, mobilizing calciferous material through rock formations. Is that relevant to this at all? In undersea conditions?
No, I don't think so. However, the question is, are these reactions I've been talking about also relevant for continental carbonates and other? No, except that there's one very glaring issue or similarity, and that's to do with the bishops from limestone. You have in the old red sandstone in this area and everywhere in the old red sandstone, North America, southern Britain, calcretes, the cornstones. And the cornstones are also carbonates that are forming within an existing sedimentary layer, which is the soil, the floodplain deposits of the old red sandstone. So calcretes are a bit like this. Calcretes are the LMAs of continental environments, but there the chemistry seems to be very different. There you're dealing with highly oxidized environments, or at the most suboxic environments, so manganese can get reduced, but not iron. And we don't see the same stratification in microbial processes in these arid zone red bed soils that we do in these settings. There are issues about the role of bacteria in making calcretes, because they may be breaking down oxalate produced by higher plants, calcium oxalate, or fungi, but we don't know all the details of that. But in a way, this intra-sediment formation of limestone beds is what calcretes really are, but they're forming within soils but in a highly oxidizing system rather than requiring organic matter and reduction taking place.
Anyone else? I've got a quickie. Is there a limit? What's the sort of maximum size of bed, diagenetic bed, that you've come
I know. In limestone marl alternations, they rarely go thicker than 0.5 meter. The thing is that you can get them stacking so closely together, they look thicker, but you'll always find some evidence of interbeds in there. And in the Bathurst model, the couplet model, again, they seem to be under 2 meters in those cases. There's a lot we don't know. Maybe if the modeling of self-organization comes up with anything, that self-organization has been used and a mathematical model presented by a physicist. No disrespect, but that model is not based on any sedimentary principles, unfortunately, but it raises the whole issue about self-organization. There's modeling going on in a Dutch university trying to resolve some of this. It may be due to diffusion distance, controls on the diffusion distance of the calcium carbonate downwards and so forth, but we don't know. But there does seem to be, yes, you don't get 20-meter beds of LMA limestones. There's something going on, but we don't understand why it stops. If you can find out why it stops, we know how it begins, why it begins, but we don't know why it stops. It could be just a sudden increase in sedimentation, so the diffusion distance is exceeded and stuff isn't diffused. We don't know. That's why modeling is important. The trouble with the modeling is it's deciding which of the parameters are the important ones and ignoring the others. And it's getting everybody on the same side that they've not ignored the crucial parameter. And the modeling has to be simplistic, of course. But no, they don't get very thick.
Thank you. Yes. Brian.
Are there any successions that go limestone silicium that are the traditional, follow the traditional model, or are all successions of that type have some diagenetic component?
The question is, are all successions that show alternations like this diagenetic bedding or not? No, I mean, the reality is that most bedding in limestones seems to be primary. Most in clastic systems where sediment is brought in and deposited, virtually all bedding is primary. But in carbonates, of course, a lot of the sediment is produced in situ. And then it gets messier, the story gets messier. Diagenetic bedding is really strictly environmentally limited. If you want to see how spectacularly limited it is, if you go to near Bridgend, just go off the M4, down to Ogmore by Sea, and to a little place called Pantaslade. There you see Jurassic skeletal sands banking against the Carboniferous unconformity. There were sands, there were shore-face sands, high energy, organic matter can't settle out, also very permeable, oxidized sediment would have been, no LMAs. The aragonite survived because it wasn't being dissolved by H2S oxidation. The rocks are full of molds of aragonite fossils. A few hundred meters away, because of a very steep gradient, because you were flooding a steep island, transgressing a steep island, you can see all the steps on the terraces and the corals attached to the steps, Jurassic corals. If you go a few hundred yards away, where there's a significant facies change, because you're suddenly in deeper water, you have couplet bedding. If you go out deeper again, but in this case, you can't walk it out, you have to go stratigraphically upwards, you've got LMAs. So, although the vast majority of bedding in limestones, as in clastic systems, is primary, there are certain environments which are associated with aragonite mobilization, which are predominantly diagenetic. The thing about couplet bedding is The beds haven't changed. The beds were there, they've just been enhanced by compaction or not compaction. In LMAs, you got new beds. They've just appeared from nowhere. They were never there. So it's very environmentally controlled. There are other issues going on as well, but the point is that LMAs are very common, and it's been a shock to discover that in certain parts of the world, they're not understood at all. And that I was skeptical of doing the questionnaire. Teresa had the idea of doing the questionnaire, and when the results were processed, and if the other way to do it is to do a data study of where papers on LMAs have come from. Hardly any from North America. Most of them from Europe. Now they're coming from the Middle East, from China, but hardly any from North America. They're there. It's just they aren't aware of it. You wouldn't think this would happen this day and age, would you? But there we are. And one of the reasons is the textbook that students have been using for 30 years doesn't discuss LMAs because they weren't invented when that. So it's my fault and Maurice Tucker's fault. We didn't put them in there because our book was published 6 years before Munica did that work. So 2 generations virtually of sedimentologists who have been brought up using that book never got introduced to it. And there's been no textbook since then on carbonates, since 1990. One of the reasons is if you write a textbook now as a young academic, you won't get any credit for it. Your head of department will tell you you're wasting your time doing textbooks. You've got to be writing scientific papers and getting grants. So nobody writes textbooks anymore. That's okay. Students don't read textbooks anymore. But because their lecturers have not been introduced to LMAs, they don't mention them to the students. In 20 odd years of teaching courses in the States, and I would discuss LMAs, I never found anybody in those classes, the oil company courses, who had ever heard of this. So it's a combination of politics, political steerage, lack of new textbooks and so forth. But they are common, they're just not appreciated in certain parts of the world.
Speaking of textbooks, and sorry if I missed it earlier, are you able to say roughly when your revised version of the stratigraphy book will?
No. We're hoping next year. We're looking for a publisher. The publisher of the previous editions is not interested because they're only interested in high volume production, not in a niche book that is in the same vein as Ager's book. It's throwing ideas out, making observations, and it's an ideas book. I don't know if you ever read Stan Shum's 10 Things We Got Wrong in the Earth Sciences. It's Ager's book with graphs rather than anecdotes. And the idea is to have a book which is a mixture of Shum's approach, why we got things wrong, let's quantify them better, and Ager's book, look at all these weird things we're ignoring. It's going to be some sort of mix of those two. And if my co-author lets me, we're going to look at not only how people got things wrong, but why they got them wrong. Because there's a lot of psychology about why people get things wrong. And letting a geologist read psychology books is a very dangerous combination. But no, probably sometime next year. Peter Burgess, professor at Liverpool, and I are revisiting, is perhaps the better, not rewriting, but revisiting Ager's stratigraphic record. And obviously this sort of thing will be in there, but along with a range of other things that have moved on since Derek Ager wrote that last edition in '93.
Well, thank you very much, Paul. That was really thought-provoking. Thank you so much. Cups of tea. I know. Oh, you have got Mike here. The kettle has not been performed.